So let's take a look at a similar problem here, where now we have multiple objects that we want to draw free body diagrams and kinetic diagrams of, and eventually we'd want to get equations of motion and solve for a unknown variable in these problems. So this makes it slightly more complicated than before. Before we just had the ground and a crate in a previous example problem. Now in this problem here, we have two different masses. We have block A and block B here. So each block has a mass M. So they do have an identical mass, the same mass as M. They have a coefficient of friction at all surface of the contact is given to us as mu. So now what that means is the coefficient of friction between A and the ground is mu, and the coefficient of friction between A and B is mu. So this is a huge oversimplification just for this problem here to make the problem a little bit more straightforward to solve. In a realistic situation, A and B would not necessarily have the same mass M, and the coefficient between A and B would not necessarily be the same as between A and the ground surface over here. So this is a big simplification just for the sake of this problem here. They tell us now that we have a horizontal load applied at P at the bottom block. So we can see at block A, we're applying this external load, we're pulling on that there with this force P here. And we can also see up top here, we've got this cable or rope holding block B from moving. So rigidly attached to the wall there. That's me pulling back in the other direction. So all of this here, we can use the information from our given problem statement and our given diagram here to do what they ask us to solve for in the problem. So the problem, again, same as the previous problem here, we want to draw a free body diagram and a kinetic diagram for each block. So that's the main difference now. We're not just doing this for one object here, we're doing it for each of these. So this is important. Each one of these will be a separate individual free body diagram and kinetic diagram associated, one for block A, one for block B. We're not going to try to draw this all into one diagram. These will be separate. So things to think about here is there may be 5, 6, 7, 20 different parts, components for larger systems. Being able to break these down into individual components, have equations of motion, have free body diagrams for each individual object is going to be important. Now, as we're moving forward, something to consider is that we may have to solve these things as a whole system as well. So you may have free body diagrams of each individual component and then one for the system as a whole. So those are things that we need to consider as we move forward. But for this case, we're going to keep it simple. I'm doing this assumption here to simplify that both have the same mass M. Every surface has the same coefficient of friction, mu. So plan of attack, similar to what we did before. One, we're going to define a coordinate system. What's a positive X? What's a positive Y? And stick with that through our problem and use that for sign convention as we're drawing out our free body diagrams and eventually to our equations of motion. Step 2, we're going to draw out the free body diagrams for each block separately, showing all the external forces acting on the blocks. Step 3, we'll draw out the kinetic diagrams for each block, showing the inertial forces. So now that we've had the opportunity to read through that problem statement and really understand everything that they've given us within the diagram and the wording of the problem, the next thing we want to do is create our setup. So in our setup, I redraw a simplified version of my diagram, block A, block B, external load P, tension cable up here. From our given information, the mass of A is equal to the mass of B is equal to M. These have identical masses. Our coefficient of friction between all surfaces is mu, so between A and the ground and A and B. And our horizontal load, our force here, is P, moving over here. So normally I would leave this as a separate page to reference back to and start my solution on a new page. But in the interest of being able to reference back quickly and point to my given diagram for you guys as I'm drawing out my free body and kinetic diagrams, what I want to do is keep it all on one page. That way I can quickly reference it for you. If I had been doing this just on my own, I'd probably do these separate and even have these on a separate page so I could draw them big and really clearly see all my forces. But for this case here, I'm just trying to keep my handwriting neat so I can reference back to this for you. So as we begin our solution, we're going to look for free body and kinetic diagrams for each block separately. First step was to establish a coordinate system. So that's exactly what I do right here. Here's my standard X, Y coordinate system. X positive to the right, Y positive going up. I didn't see any real reason to use anything different to simplify down my solution, so I'm going to stick with my standard and go with that there. So, I want to deal with each of these separately. Let's deal with just block B. So the top block, block B, what are my external loads acting on this? Well, I have this tension force from my cable right here. I have the weight force acting down, W sub B, which is my mass times acceleration due to gravity, acting my negative y direction. I have a normal force of block A pushing back up on block B right here, and I have a frictional force opposing the direction of motion. Now, this is where it gets a little bit tricky, and we really want to think of moving the system in our mind, because our frictional force opposes the direction of motion. What is the direction of motion of B? Well, B really isn't going to move because of this here, but A is moving in our negative x direction, so technically B would be opposing that motion relative to A, it'd be moving to the right, in our positive x direction relative to A. So our frictional force on B would be opposite to that direction that it would be opposing A, which would mean our frictional force is going in our negative x direction right there. So I know that gets confusing, but it opposes the direction of motion of the block that we're dealing with in drawing the three-body diagram. Now, we'll go over this again when we talk about block A. So now all of our forces are acting on this, our weight force, our tension force, our normal force, and our frictional force right there. We do the same thing now for block A in the bottom. So block A in the bottom here, what are my loads? Okay, I have this external load P now acting on block A. I have my normal force from the ground acting up right here, and sub A, I'm calling that there. And I have my weight force of A coming down here. Now, the difference is that there's two blocks. We also have the normal force of B. So this is the common factors between block A and block B, as this normal force A, or normal force B in between the two, and these frictional forces right here. Because A is going to have two frictional forces acting upon it, because there's a coefficient of friction between block A and block B, and a coefficient of friction between block A and the ground. Now, luckily for simplification purposes, it's the same. They tell us that that's just mu. Reality is probably not. This could be a different frictional force, different surfaces, different materials. So that means block A has a normal force of B acting on it, a weight force acting on it, a frictional force on the top between A and B acting on it, and a frictional force on the bottom between A and the ground acting on it, as well as this external load. So there's a lot going on. So like I mentioned earlier, you really might want to draw this out as a bigger diagram if I hadn't been doing this just as a sample here. So all of these are my forces, and where that does get complicated quickly is when we start taking this to the next level for our equations of motion. So again, frictional forces here are going to oppose the direction of motion. Direction of motion of A is going this way. Our frictional forces go this way here. And one more time just to highlight this, as we move forward and we're coming up with equations of motions, we're going to have more unknowns and equations. We're going to need to relate the equations of motion of block A to the equations of motion of block B. And these common surfaces between A and B and those frictional forces and normal forces are going to be the things that allow us to relate those two sets of equations. So that was step 2 in our solution. Step 3 in our solution was to draw out our kinetic diagrams here. Summation of forces equals mass times acceleration. So there's our MA here, direction of motion there, direction of motion there. This is actually 0 because it's not moving. It's static, it's stationary. So this is 0. And we draw an arrow in here, but it really doesn't matter because it's not moving. There is no direction of motion in either way.